Now, I bragged about you yesterday, so you need to be very good today. The man I'm working with in CAM said at the last spring class, the students didn't do a very good job responding to the talks. And I said, well, that's not true of my ENGI600 people. I said, last week I told them we didn't even need to be here because you were doing so well responding specifically to the talks. So do that again today, please. That's called a pep talk. Right? You may begin when you're ready, Chow.
So I'm going to finish by
Does he know
11:10.
Yeah, I talked to him.
I'm sorry?
I'm going to finish by 11:10.
Yeah, perfect.
Okay. Our speaker today, and also the very last speaker of this class this semester, is Gabriel. It's Gabriel Pilato. He's been working on developing new communication strategies for mobile devices to provide faster access to the internet for almost every one of us. That being said, let's welcome Gabriel.
Thank you, Shao.
Yeah.
Today I will show you how my research will help you to lose less time using your mobile phone. Well, when I was sitting there, I was trying to be calm, and I was looking around, and with exception with Dr. Hewitt and Judo, all of you were checking your phones. Probably you are using one of these applications: Facebook, Instagram, checking emails. So these are the most common mobile apps we have today. And as a user of mobile phone, this is how the internet connection is used in your phone. Of course, we have the most common applications are the social networks today. But no matter which kind of application do you use, probably you have faced some problem waiting for the page to load or waiting for a video to be ready to watch. So today I will show you how my research will help to reduce this time to get data ready for you. So I have an example here. Probably if you are a user of YouTube or Netflix, you have faced this situation before. It's bad, right? You have to wait for buffering, and it's a bad situation, right? But, well, do you know why it happens? Why Netflix buffer? So I will explain you this and show how I can help you. But before, I have to show you how your mobile phone works, how the data gets in your mobile phone. So in the past, probably you just use your phone to make calls. But today, with the social media, you have access to data. So probably you have a plan with your carrier that you contract an amount of gigabytes for a month, and this is probably your contact with what do you know about data. Probably you have 1 giga, 2 giga, or 10 giga per month to use. And for example, all the things that you do in your phone are data. If you access music, a video, everything is related with data. And for example, 7 minutes of high definition video correspond to 1 giga of data. But how this data arrives in your devices, in your tablet, in your phone, your smart TV, or personal computer. So the way the data gets in your phone, it's by waves that comes from the air, and these waves carry a certain amount of data. And this data, these waves are sent by a station we call a base station. All this device has to access this data and in different times. So the waves flows and the data gets in your phones. In order to be served for this data get in your phone, you have to has to be in the coverage area of a base station. And the problem is this coverage goes from 100 of meters to tens of square miles. So you probably are not alone in this area, and you just have you have a base station that has to serve multiple users, and this is why you have to wait. I can do an analogy here with a restaurant. You have the attendant that has to serve a certain number of tables, so you have to wait. And if the service is not good, you probably not come back to that place. But how to solve this problem? It's the same in the data with wireless communication. You can increase the number of attendants. So probably you have better quality. You have to wait less time. But what's the problem with this? It's not a cost-effective solution. You will spend money, and for example, a base station costs more than $1 million to build a new base station. And if you build new base stations, probably this problem will happen again, because as the number of users and the number of devices that each user has will increase. So in my research, I propose to reduce this time to waiting for data by, instead of transmit one signal at a time for each user, transmit multiple users. So the idea is to send 2 waves of information at the same time with different information for each user. But the problem is, when I do this, transmit 2 waves at the same time, the waves will interfere in each other. So the challenge is overcome this interference and make a system that is able to be simple, that we can use in a mobile phone, in a tablet, and in the base station. So the inspiration for this, my solution came from several years ago. We have 2 signals, 2 streams of data to send for 2 different users. So if you just broadcast this information over the air, we'll get the signal will combine and will interfere, and the signal that will arrive in each user will be useless. So the idea, we can see here the received signal is different from the transmitted signal. We can not get data from this. But if you have some feedback of the channel, if you know how the channel mix the information, we can adjust our information before sending, and then we get the perfect signal that we want. We call this pre-coding or pre-processing. We are adjusting the signal, and so we get the same information that we know for each, we want for each user. In my work, but this solution is really complex. It's it consumes a lot of time, and it's not, I cannot use in a mobile phone because it's really complex. So in my work, I propose a different approach to deliver 2 in streams, reduce the complexity of that method, and that method is optimal, what means that no other solution will reach the same result. And there is a simple solution, there are other proposals for a simple solution, but they don't achieve the same results. So in order to solve this, I propose to reduce complexity using Let's codes that want a mathematical structure, and to overcome the suboptimal results, we do a right allocation of power. So this is my idea. My scheme is like this black box. We have our 2 streams is our input, and we have to, as an output, the 2 waves ready to be sent out by the base station. So we have to do 3 steps in my precoder. The first, reduce the interference that we need. Second, allocate the right power to achieve the best performance. and reduce the channel effects is how the waves combine and how they lose power as we transmit them. So this age is given by the feedback that we suppose that we have. So we have to figure out which is A and D. So look inside the black box. This is our LEDs codes. We map the information in the LEDs, and then we pre-code this information and send our waves. And I have found analytically the expression for A, this matrix, with just a variable, and the D is another matrix with two variables. And with this information, we build our pre-coding matrix. And this solution is completely analytical, and we can implement in an algorithm. It's really simple. And this is our results. In the left side I'm comparing with the optimal solution. In the x-axis, I have the power available. As I increase the power, I can send more information. In the y-axis is the information. But what is really important is the right side. I show the gap, what the gap is, how far my system is from the optimal. And we can see here that we are 0.1 bits far from the optimal solution. That is really good. And I have different methods to find this pre-coding. So the contribution of this work is to propose a scheme that is feasible to be implemented in a mobile phone, in a base station, that can allow us to transmit two streams of information at the same time. So when the information flow, people learn and countries grows. Thank you.
Let's thank Gabriel for giving us this wonderful talk, and if you're asked to ask a question before that, now's time.
So, I have a question. How far are you from how far is your research from actually being implemented?
Well, this is a good point. The first.
Remember to repeat the question.
Yes, I'm sorry. Julia asked how far we are from the theory to practice to implement this. Well, the first step is these LEDs codes that our work is based. It's really good, but it's not feasible yet. Because we consider it's infinite LEDs, and this is not feasible in practice. So we have to use small LEDs, and these small LEDs still has no good performance yet. So one point is this. Another point is the feedback that the channel, but this is completely feasible today. This feedback that the user sends to base station. All the other schemes already use this. So the major point is build LEDs that are good enough to be used in practice.
Another question. So in your results page, you said you're comparing to optimized solutions. So how do you define the optimized solution?
Well, Chow's question is how to define the optimal solution. The optimal solution is that solution that get the best results. You cannot go beyond. For example, in our case, the highest capacity of the channel is use this scheme to send two streams at the same time. So any other solution just will not go beyond these results. You at most reach these results. And for example, it's what I can show here. If my scheme is here, touch 0, we are touching the optimal solution. This is why we have this gap from the optimal.
So it's theoretically possible, not cannot be achieved in a practical way.
No, can be, but for now, this is only theoretical. And our scheme, for example, is not optimal. The way we choose this matrix, we can even improve this to try to better results. But we consider that the results for now, it's really good. It's already good.
Let me stop and inject a point here. And I apologize, I've never talked about this before in this class. And that is, the introducer should always be prepared with a question. So that if there's that dead spot after a talk when nobody asks, and here Yulia was assigned and she gave a good reasoned question. But always the introducer should have a question prepared so that the speaker, there's an immediate engagement. Right, back to you, Chow. Okay.
Still on the results, can you explain what those different curves?
Okay.
DPC, high, SNL approximate, I'm kind of like, I don't know what they mean.
So the bigger question is which are the other results? So the DPC is the optimal solution. It's the theoretical and that's complex solution. All the other solutions is we developed them. For example, the red one, it's a global optimization. We are just using a reference. Because the way that we implement this, it's not, how can I say, it's not useful to use, but we can achieve this solution. But all the other three solution is our solution. The green one works better, as you see, for this range of power. As the power increase, this solution is getting even better. And in this region for low power, it's outside the what we consider good. But the other solutions here, the blue one and the yellow, performs really well for low power. But as the power increase, they are losing performance. So our scheme depends on the power we have. We select one of the different schemes. But the green one is that completely analytical. And the blue and the yellow, we use some kind of optimization. It's not really analytical like the green one, but all the three are results.
So basically that green one, it looks like it's cut somewhere.
Yes, because here just because I give a zoom in but if you see here, the gap is really huge for a low SNR.
Oh, I see.
It's still good, but it's more than we consider because we are cutting 0.25, 27.
Yeah,
that is the analytical solution we have.
Yeah, because my confusion was I was trying to figure out where is the data for the green. Why?
Yeah.
So I think now that you've mentioned, you've zoomed in now.
Yes, and the problem is I still generating a result for this range. This is why my simulation is still running right now to get the new results.
Oh, okay.
Excuse me. And in which point are we today? I mean, the real application in which?
Depends.
Okay.
Depends. The best region is the high power, because in high power you can send two streams and they will not interfere as much as low power. But the problem is in low power, and in low power is when you are far from the base station, or mainly when you are far. So depends where you are. You are in the same situation, in the different situation.
Okay, we're done with questions, so let's move on to our topics. So we have asked a lot of questions. So B, focus the talk, Peter.
I like the focus. The focus of the talk is really nice. The research problem is clearly defined, and the way he was using, he used the basic explanation. Even anybody who is not from computer science understands what's going on.
Did you understand
Which is
this
really,
time?
really good. It's really good. I like it. So should I go with the context also?
Yeah, go
Yes. Also the context was because he compared with what other people have done, and people have the solution which has been there, interference and everything, and then the cost which involved, which is kind of like really cool.
Thank you, Peter. And next week we'll go to the importance of the work. Yulia.
Well, he spent a lot of time motivating his work, so the importance was very clear, and we can all relate to it. I deal with internet on a daily basis that loses power because there's an interference. So if this can be fixed, that would be wonderful.
Very nice. So method and results.
So I think it's a very good talk. I mean, Gabriel really spent a lot of time to do the motivation, so I think it's really good. And I think the method is to implement a lattice code with additional benefits from power allocation, right? For the interference management, and should I also go with the results?
Yeah.
Okay, so the result is that I assume in simulation, with the simulation, Gabriel has demonstrated that the performance of the proposed strategy can achieve to something close to the capacity with 0.1 gap to the data paper coding. Yeah, just one kind of suggestion here. So I think there is like some previous work on the lattice code, also on the interference part.
Yes, yes.
Yeah, so I think maybe, I mean, in the final paper you can put some lines
Okay,
here
yeah,
compared to the previous
yeah.
art.
I forgot that you mentioned computer for it.
Yeah, sure.
Let's
but
go
I
to
mean,
computer
it's
for-
a
yeah,
very good
yeah.
topic. It's very clear, I think, even for the non-com people.
And I guess she has just covered the unique contribution that Gabriel had developed a new lattice algorithm to optimize this data transmission speed. And next, let's move to possible applications.
Yeah. It's very clear. Like that was really nice, and the application is just to apply that to the base that we have today to make the information more available faster and at the same time, so it's clear. And I keep on going.
Yeah.
Okay. I think the opening sentence was so good because we were like, oh, we can get more buffering and like, let's show us how we can be like so comfortable using data. Sometimes it's a pain. And for the closing sentence, it was good, but a little bit too long for my taste. So I only take the last phrases that it's we learn more, and because it was too long, and I didn't know if it was the end or not.
Okay.
But it was good.
Thank you, Han. And let's move on to one particularly good aspect and one suggestion for improvement. Jojo.
Okay, so I really like the visual of the slides, especially when you introduce the concept. It really helped me because I'm not a computational specialist, so I understand the concept very well with the help of the graphs. One suggestion for improvement is also on this because I find some graphs are quite distracting, like the baby face and like the mother feeding two babies in
Yeah,
those.
okay.
I kind of have to use my willpower to focus on your slides instead of all those funny pictures. And also from the beginning where you show a lot of different apps and those, it's like a busy slides.
Okay.
Where I think you might not need so
can't read
many
that.
examples.
Okay.
Yeah, this one. It's like what's going on. But yeah, overall it's really good.
Thank you.
Yeah, so, and Jojo has just covered a lot of qualitative slides, so I'll just add a few. So in this, in addition to busy, the words, the text on the right panel is a little bit too small, so we probably cannot figure it out. I can figure it out, but I'm not sure.
I can't.
Probably not. And this also happened to some other of your figures, especially your result page. Those like X labels and Y labels are too small and they are kind of gray, so I think I don't can figure that out. And I do like these one mother feeding two babies at one time. So that's demonstration of one station giving stream to multiple users, and I do like that one. And page number 8, a little bit too wordy, I guess. So page number 8 is talking about your goal, and it's good, but it's a little bit too wordy because if you look at right panel, second dot, it says solve complexity issue by using recent result on lattice code, and I guess that can be somehow trimmed a little bit.
Okay.
And I do like your explanation before and after you define or you introduce a technical term. That helps us a lot in understanding your research. indeed some of your slides are a little bit busy, but you use good animation to walk through those slides so they don't seem that busy during your talk.
Particularly like the animation where you got the base station and you kept adding users. That was,
That was really cool.
it not only was visually interesting, it actually demonstrates what's going on.
And what's the problem?
And it's one of the main points he's making.
And you can make that number 1,000 bigger.
Yeah.
So basically, one quick question: are you trying to make the base station smart?
In some way.
Smart.
It's already really
because
smart, but we can.
Yeah, because right now everything people say is just smart because they know the way they were designed back in the days. You know, they never used to intelligently make decisions, you know, by themselves. So now it's kind of like people want to design them and make sure you optimize them as much as possible.
Yes, yes.
So you kind of like you make them like, you know, have some sense of intelligence or something.
Yeah, but as I said, if you have to, for example, to have feedback, without this feedback, you cannot do anything. And for example, these smart things, you have to have some input to do the things act smart.
Yeah.
And this is one thing here that we really need. But in some way, and for example, last week should talk about the smart antennas and the way we send information for each side, and this is something related with this in different contexts, but we are trying to improve that.
What's the time trade-off between feedback and sending, receiving signal? So is it slowing you down by having feedback, or is it insignificant that you shouldn't even worry about it?
Well, the amount of information that you need will determine the quality of the what you can do. So, for example, in today's use, we are sending and receiving information at the same time. So it's not a big problem to get this feedback. But of course, the feedback will reduce the rate that you can transmit, and the rate is really it's a constraint in your system.
Okay.
But the time is it's really small. It depends on how accurate you want to sense in your channel.
Thank you. Very good.
This is just curiosity, like how do you get the experimental data? Do you have like many bases in
In
your
this
lab?
case, in my
Yeah, like I don't know how.
in my case, it's just simulations, mathematical simulations, and
Okay.
we try to model the whole system and generate, for example, random channels and get data in this way. The next step, of course, is use some kind of hardware and put some software to do this.
Okay.
But it's far from my case. My case is just doing codes and.
Okay.
and
Computer
simulating.
Don't say just doing code. That minimizes your contribution.
Okay, sorry. Yes.
Doing code.
Yeah, I'm doing code.
Yes.
That's, so you see that? I don't understand that. I don't want you ever to say, "Well, I'm just." It's like saying, "Well, I'm just a housewife." Something I want all of you to notice that worked extremely well here, and that was the comparisons, the analogies, to show the twins, to show the two streams, to show the interference with the crying baby. And I think particularly important was the waiting time for service, where there are too few waitresses, and then if you want better service, you go to the white tablecloth. We've all been there. The white tablecloth, and the number of waiters increases, but the dinner price is also going to. You walk in and it's a white tablecloth, you know, well, my bill just went up X number of percent. And there are days when you want to do that, but days not. And what happens then, because of those analogies, you got through the basic ideas to the broad audience. Then he also got enough specifics in there to appeal to those of you who are in the field. But it didn't bother those of us outside the field because we still had the general overview. Am I right, Ju? Okay. You look at this, there's not any jargon up, because I don't know what dirty paper code is. That's the only one I'd question. But signal, pre-processing, simultaneous, transmission, interference, those are all generally understandable terms, and yet they're true terms. So he worked very hard to translate what was going on in the field to the audience that he was supposed to be talking to. So it's a very fine way for you to end the semester for us. Thank you. Comments?
The one thing I wanted to say is that I liked at the beginning, you gave us what we call a little forecasting statement. Before I can talk about my research, I need to explain to you how your phone gets data. And so we're sitting here going, okay, we know what's coming, and it's so much easier for us to absorb. So that kind of thing is helpful.
It's just like when you're writing the abstract, you get that claim up front. And you're doing the same thing in the paper. I've been very, very pleased with you as a class. You have learned a lot, and you have contributed a lot to each other. And one of my colleagues the other day was saying, well, if the students just respond, you know, what good is that? Well, come to my class and see, because you're good. Now you know what to look for, what to listen for, how to respond. And you can make very specific comments and be kind doing it. And that's the goal we have had for you. So I applaud all of you right now, including Gabriel. Notice on your syllabus, no homework next week. Even better than that, no class next week. Thank you. No class next week. Because Thursday is Thanksgiving, the university is closed. Because there's no Thursday class, I felt totally justified in canceling the Wednesday class because we do the same things, right? So, and then the next week is the last class of the semester. Your big deal is due on Monday, the 23rd. What is it, 4 o'clock? I will be in my office to get those next week. If you need an extension, you've got to ask soon, folks. And if you're ready to meet with me before then, let me know. I'm meeting Alessandra tomorrow and Nick the next day. But anyway, okay. Any further questions here? Okay.
Thank you.
If you would hand all the here. Okay.
Yeah, I think I have.
Let's go to transitions. Only one comment, Ju, Chow, on your introduction. Don't turn and read the name off the screen. Have it in your head. You remember Gabriel, but you had to look at the screen for Bavaro.
Yeah.
Yeah. Thank you. You're taking care of it all. All right, transition. Trans means across, and it means a bridge. So transitions in your writing are essential, and in your speaking, as Gail pointed out about before I do this, I've got to do that. That's a bridge from one idea to the next. Helps move your reader along through what you're writing. It helps the flow from one sentence to another, from one paragraph to another, from one section to another, from one chapter to another. You've got to have transitions in place for all of those. If, and we've mentioned this before,